So I showed this off a few days ago, and one of the main improvements I've made since then is switching from using a microphone as input to using raw sine wave oscillators as input. And this gave me a lot more control to really fine tune how it worked and make a much better demonstration of what it's doing. And so what I'm going to do now is I'm going to make an oscillator running at a 300 hertz frequency with a 40% amplitude. And what this means is that the sine wave that it outputs is going to oscillate 300 times per second with an amplitude that's 40% of the maximum possible output amplitude. So you can kind of think of amplitude as the volume, right? And the frequency is the pitch. So if I look at what this looks like, what you're seeing here at the very top is called the time domain waveform, because the x-axis of this visualization contains the time, and the vertical y-axis is the amplitude. We can see that it rises and falls to about 40% of the height, hence the 40% amplitude from the original input. It's a little harder to see, but with such a simple waveform, if I just disconnect for a second and pause it, right, you can see that there should be, if you actually count them up, there should be 300 peaks and 300 valleys per 1 second of this waveform, which is what you're looking at here is 1 second. So I didn't count them, but there should be 300 there. uh, However, this is not really an explicit dimension of this visualization, right? It's something we can do only because the data that it's showing is so very simple. And it would be, as we start to look at more complex waveforms, you'll see how it becomes kind of impossible to sort out the frequencies. But if we look at the histogram below, what this is called is a power spectrum histogram. And it's the result of taking the distributed Fourier transformation of a window over this top time series waveform. And what you see here is each of these bars represents a band of frequency. So this bar that's really tall is the bar that represents 300 hertz. Uh, and the x-axis on this visualization is essentially frequency, and the y-axis is still the amplitude. Okay, so it looks like this is not showing a 40% amplitude, but in order to see that, what I need to do is I need to make the waveform a little more complicated, right? So I'm going to go ahead and add a 900 hertz oscillator running at 80%. And what you can see here is that there is a difference between these peaks, right? That this one's about 40% and this one is now the tallest peak, even though it's only 80%, it's the tallest peak. So it's kind of relative to the tallest, right? It's just the way that this visualization happens to work. And if you look back at the top, you can kind of see this is still a pretty simple waveform. You can see there's like, a smaller oscillator inside of a bigger oscillator. But it's starting to get more difficult to see what's going on, right? And when we look at really complex stuff like speech and music, you won't be able to make any sense out of the frequencies in that, right? Which is why it's so important to have both of these visualizations, right? Again, one being focused on time and the other being focused on frequency, and then both of them having amplitude on the y-axis. The last thing to talk about is this visualization at the bottom, which is called a spectrogram. And what it tries to do is put all three of these dimensions, amplitude, time, and frequency, all back together into a single picture. And the way that it does that, so if you imagine this middle visualization, the power spectrum power spectrum histogram, and you imagine that you kind of built a three-dimensional model of what's on that, and then laid it out continuously for the entire duration of the audio. And then you took a helicopter or something and flew up over the top of that three-dimensional model and looked down at it. What you would see then is the peaks, is each one of these peaks, and that's what you're seeing in the spectrogram, these bright lines. The bottom line represents the 300 hertz peak, right? And the higher line represents the 900 hertz peak, and it should be slightly brighter, right? That 900 hertz line should be brighter than that 300 hertz line. It's maybe a little hard to see that. This visualization might need a little more tuning there. So essentially in this visualization, the x-axis is time, the y-axis is frequency, and then the brightness, the z-axis, looking down on it, the brightness of these lines would be the amplitude. So if you play something really complex through this system, right, what you can see at the top, there's nothing that, like, you can't pick out frequencies from that. This is what I was saying. As the waveforms become more complicated, even though the waveform is still the sum of lots of simpler sine waves, you can't really see what's going on anymore, right? And in the visualization below that, you can see what's going on at a point in time, but you can't see the bigger picture of the entire waveform. So it's only in this bottom spectrograph, right, that you can see all three of those dimensions at the same time, right? You can see a chunk of time on the x-axis, you can see the frequency distribution on the y-axis, and you can see the intensity of each frequency based on the color. Okay, and this is what is actually the basis of machine model training, right? These spectrograms, actually you see them in a lot of places, right? It kind of reduces audio recognition to an image recognition problem. Oh, and you kind of see them in other places too. If you think about like how a music box works or a player piano, right? You see very similar. They kind of store their data on a similar medium, like a tape medium that has raised bumps or holes or something to represent various, tones, various frequencies. Uh, so it's actually really interesting that you've kind of reinvented a music box by going through all this math. But you can essentially take this could come from a microphone or from a sound recording, right? And you can get back to, something that's very, explanatory and very recognizable, right? And this is the kind of inputs that can be used to train machine models.